Good afternoon, everyone. Our team is formed by Carlos Lopez, Jacqueline Aguilera, Eduardo Camacho, and your servant, Ana Paula Venegas. And today we are here to talk with you about aquatic organisms that can reduce the pollution. The problem to solve is the case number 2 that say that Oaxaca is a Mexican state with textile industry. Natural and synthetic fabrics have to be colored with aniline-based strainers. The dye excess is discharged to rivers, affecting the environment and causing some problems to the organisms. Before to begin with the solution of the problem, we need to know about what is aniline. So, what is aniline? Aniline is a oily, colorless liquid. When exposed to the air and lighted darkness, it can also be a solid in cold temperatures. It has a pungent odor and a burning taste. It is soluble in water. It has been identified in various foods and in tobacco. Aniline is an important commercial chemical. It is used to make dyes, rubber additives, drugs, photographic chemicals, pesticides, and other compounds. This chemical appears as a yellowish to brownish, oily liquid with a musty, fishy odor. The melting point is -6 degrees Celsius. The boiling point is 184 degrees Celsius. The flash point is 70 degrees Celsius. It is denser than water, with a density of 8.5 pounds per gallon. The risk of this chemical is that aniline is a skin and eye irritant, damage to the blood element hemoglobin, resulting in decreased blood oxygen levels, can result from exposure to high amounts of aniline by inhalation or ingestion. Blue lips, fingernails, and or skin may occur due to the decreased blood oxygen. Dizziness, headaches, irregular heartbeat, convulsion, and death may also occur. This same effect may occur from exposure to a lower amount of aniline over a greater amount of time.
So, what can we do? The objective is solve the problem of water pollution by aniline and try to reduce pollution using aquatic organisms or products derived from their metabolism.
How do we express our identities? Is it by the clothes we wear? Or what we decorate our homes with? Or the accessories we carry around in public? What do these all have in common? They're all made from textiles. The textile industry has woven itself into our everyday lives, most notably in our apparel and home furnishings. It stands as one of the oldest and most lucrative industries, predicted to be worth $2,100 billion by 2025. But as successful as the textile industry may be, it is also one of the most environmentally taxing. Before you can buy your t-shirt at the store, textiles must go through a long supply chain, from the farm to factory to factory. First, raw materials must be acquired, then weaved, dyed, and finished with chemicals until they're exported for further processing. Although scientists and consumers have begun to point their fingers at the fast fashion industry for excessive textile waste, the entire textile industry is responsible for global scale pollution due to its excessive water consumption. For example, the agriculture of raw materials like cotton consumes an unsustainable amount of water and pesticides. But an even more alarming form of pollution comes from textile dyeing. The dyeing and finishing process directly account for 35% of all industrial chemicals released into the environment. Think about it this way. It's 200 to 700 liters of water to dye 1 kilogram of textiles. Now let's look at 2025, where the textile industry is predicted to produce 100 million tons in textile fibers. See the problem? If you were to take a cup of this dyed wastewater, also known as effluent, it would likely consist of concentrated dye, salt, chemical auxiliary agents, and heavy metals. None of this is good for the environment. Dye effluent is toxic, carcinogenic, and has a low biodegradability, meaning it's almost impossible for it to break down on its own. If released into the environment, this salty, sometimes acidic, colored waste increases water turbidity, meaning less light can pass through it. This decreases the ability of underwater plants and microorganisms to undergo photosynthesis to create oxygen, thus increasing chemical oxygen demand, COD, and biological oxygen demand, BOD. With less oxygen, less organisms can be sustained in the polluted ecosystem. The reason why dyed water is so harmful to the environment is due to color-emitting portions of the molecule called chromophores. Chromo, Greek for color, and phore, Greek for carrying. The Phoenicians were the first to yield the use of these chromophores as early as 1570 BC in creating royal Tyrian purple out of predatory snail shells. 3,000 years later, in the 19th century, would William Henry Perkin synthetically create a dye called mauvine, or Perkins mauve. This would lead to the departure from natural dyes to synthetic ones, due to their greater color diversity, color intensity, faster dyeing time, and cheaper price, even if it's at the cost of the environment. So why is this mess so hard to clean up? Dyes are large compounds that get their color due to the derivatives of this guy, benzene, and other aromatic rings. Benzene is a 6-carbon ring with alternating double bonds. In this ring, if energy, say a ray of sunlight, hits it, this ray of light causes the electrons that were once in their ground state suddenly forced into an excited state. Now let's look at this synthetic dye with a lot more double bonds and rings. While this molecule looks big and scary, it's responsible for this beautiful color. The more double bonds next to each other, the more places your electron, like a ball in a pinball machine, can bounce off. The longer you can sustain your game of pinball, the more likely that your compound will emit a color that we can see in the visible spectrum. Synthetic dyes often dwarf natural dyes in size. The more rings and double bonds, the more stable the dye is. These rings give the compounds a strong, stable backbone, so the compound is happier when bonds get to stay together rather than broken apart. This makes synthetic dyes impervious to sunlight, bacteria, and physical weathering, as opposed to smaller and less stable natural dyes. This durability, while great when trying to dye a fabric cheaply, makes dye compounds harder to degrade and clean up.
His proposal, our company, the Oyster, present has a solution of this problem based on we base this problem on replacement of the aniline with a pigment of aquatic origin. In this way, canceling out the pollution and forming a more environmental friendly company and improving in all the ways.
Algae can be the solution. The algae could become substitutes for the current synthetic dyes, which will avoid the contamination of the wastewater that is generated during the dyeing, thanks to the biodegradable nature of these plants. When synthetic dyes are used to color a textile, some of them are not retained by the fibers and go to the wastewater, polluting them. Why replace aniline instead of degrading it? Based on previous research, the bibliographic sources only present information on pathogenic microorganisms with the ability to degrade aniline. Currently, we don't have the information on probiotics or beneficial organisms with the ability to degrade aniline. Only pathogens such as Enterobacter dissolvens AGP1 and Pseudomonas aeruginosa AGP2 achieve an 96% dye removal, 100 milligrams per liter in 6 hours. But these pathogens cause diseases not only in humans, but also in fish. Naturally, they are already found in bodies of water, so their use for the biodegradation of pollens is not recommended unless they are subjected to genetic manipulation to transform them into non-pathogenic. It is a it is a very advanced procedure and we don't have the equipment to do it industrially. We are in Mexico and we don't have the capital or the money to do it.
The color that can produce from algae are from algae had glycolins are whose chemical structures produce the color blue with red fluorescence or reddish with orange fluorescence. Um, the glycolins also contain carotenoids and cataxanthins, axanthins, and SHA1. Spirulina, uh, in this case, is blue, green color in the presence of chlorophyll that give it its green color and phycocasein, a pigment that give a bluish color. An individual blue extract can be obtained from this. The algae of interest from adaptation of this pigment are rhodophytes, cryptomans, and glaucosystophytes. The Rhodophyta division is characterized by having a reddish color resulting from the dominance of the pigment pyrrokeratin and phytococaine, with mass of chlorophyll A and beta-carotene and other xanthophytes. In the case of Christophids, comprise a group of flammentating unicellular organisms present in marine and continental waters. Individuals are flat with the viral symmetry, most photosynthetic, and this with a single chloroplast with a central pyronode. Phylloproteins with the tylodes are present in this algae is the xanthophyte and beta-carotene. And for last, the Glaucosystophytes. This is a small group of unicellular algae that present endosymbiotic cyanosymbiotic cyanobacteria, called instead of chloroplasts. Cyanols are considered as an example of the first step of endosymbiotic theory of the origin of the chloroplast. Um, you can obtain pigment like beta-carotene and beta-carotene and xanthophyte. The advantage. Natural dyes from macrochemical algae have three advantages. These are obtained from renewable source. This source act as a sink for CO2, and the water waste obtained for the process with algae is less polluting than the normal process. In addition, the use of dyes made from algae reduces the need for the process to purify water, and microalgal pigments can grow quickly under controlled conditions, leading to high productivity and produce hourly to no matter the time of the year. And the extraction or purification of the algae. The methodology was based on the work carried out by the research department in Polymers and Materials, University of Sonora. This work was based on the extraction of phytocholine from the microalgal cell of Dorosus marinus microalgae by implementing manual fermentation and sonification. The purification of this same is carried out by the precipitation process making use of ammonium sulfate and excluding chromatography by and anionic agent. The preparation and fractional of the crude extracts. The algal cells were risen with 0.01 mol nanosphate buffer containing zero point 0.1 mol sodium chlorine and at pH of 7 and were suspended in sodium phosphate and sodium chlorine buffer. The suspension was then frozen at minus 20 centigrades and sonicated for 30 minutes, and cellular fermentation was performed manually in a ceramic pot. Cell debris removal was achieved by centrifugation at 5000 rpm at 4 centigrade for 10 minutes. The supernatant was referred to as a crude extract, and the precipitate was discarded. The crude extract obtained was saturated with 40% ammonium sulfate, heated for 3.5 hours, and left at 4 centigrades under precipitation, and the centrifugate at 3000 rpm for 10 minutes. The precipitate was discarded. The supernatant was saturated with 60% of ammonium sulfate, agitated for 15 hours, and left at 4 centigrades until precipitation, and then centrifugated at 3000 rpm for 10 minutes. The precipitate was suspended in sodium phosphate and sodium chlorine buffer. In the case of the chromatology, the remaining ammonium sulfate was removed by chromatology on a Cefax G25 column pre-calibrated with phosphate buffer containing sodium chlorine. The separation of the fragments uh, with the infraction of the elevate. These were separated in chromatology of column and in a HPLC system. The column was elaborated with sodium phosphate, sodium chlorine buffer, and the elevate was collected in 1 millimeter fractions.
Conclusion: synthetic colorants are efficient and economical, but with a high degree of toxicity, whereas natural colorants are very efficient but, with a higher cost due to required production process. With everything mentioned in the presentation, it can be said that they promote the use of dye derivatives from seaweed, which are fast growing, with that we can help a little to reduce the contamination of water, which are highly polluted with a toxic waste generated by artificial dyes such as chemical agents and other substances, which can take longer to decompose, directly affecting the flora and fauna and pollute water, and triggering more environmental problems just for the simple fact of the use of synthetic colorants. Such a simple action can attract such complex problems.